Hi everyone. In this video on the kinetic molecular theory, I want to highlight this idea that we tend to use computer simulation to learn about particular microscopic system. And what I want to do in this video is to have you go through a particular simulation that's based on the kinetic molecular theory and have you go through them and see that the simulation allows us to explain the relationships that are observed in the empirical laws, okay, Boyle's law and so on. This is really a fairly common practice these days because we have computer technology. You can basically program a particular mathematical equation or several mathematical equations into a computer program, and afterwards you can run these simulations to create different types of events, and that helps us understand what's going on microscopically, and that allows you to make further tests to test your hypotheses, okay? And a lot of these come under the label molecular dynamics or MD simulations. You'll hear this more often if you go further into chemistry or into physics. These type of simulations are run so that you can then come up with new experimental ideas. Okay, so the particular simulation I want you to try to understand is available from this website from Oklahoma State. You can go there and play with it yourself using your own computer. I'll go through in the video and then run through a couple of the setups for the experiment of the simulation so you can actually see how it's done. The goal here is to use the simulation to explain how we get the empirical gas laws, how we can explain the empirical gas law. Why is pressure and volume inversely related and so on, okay? So we want to relate what's going on microscopically in the simulation to the macroscopic laws that we already know, Boyle's law and so on, okay? And the goal is really to answer the following 5 questions. Why is Boyle's law observed? Okay, in other words, why is pressure times volume equals a constant? Why is it that when pressure goes up, volume has to go down when temperature and number of moles are constant? Can we explain it using this simulation? And all of these questions there you have to answer as well. Now, next to the video, you'll have a form. The form will basically ask these questions or some of these questions based on the simulation, okay? So what I'm going to do now is go to the simulation. Okay, so here's the simulation. It's fairly simple. It's basically simulating a collection of gas particles. Here, all of these are green. I'm going to pause this a minute so you can see that all of these are green particles, and they're modeled or they're simulated using that kinetic molecular theory model, which is that these are hard spheres. They have elastic collisions with each other and with the wall, and then there's a certain volume here. The volume is given as this is the volume of the container. You have these gases here, and then we have a plunger that allows you to kind of change the volume up and down, and then the gases are just moving around randomly as you saw earlier. So if I just continue this motion, I click here, that allows the gas to move back and forth, and there's all these parameters here that you can use to change, okay? So for example, if I leave the marker here on the pressure, okay, so you notice that there's pressure, volume, number of moles, and temperature, and number of moles are for 2 different gases, helium and neon. Right now we are seeing helium at 1 mole, pressure is at 1 atmosphere, volume is 22.4 liters, and temperature is 275 right now. I can see what's going on with a particular parameter if I leave that mark over there. So in other words, pressure right now is marked, right? With this, I can move it here to volume, but right now let's say I mark pressure. So if I were to change volume, the pressure would change correspondingly. Everything else will be fixed. So in other words, the only thing that's changing is the pressure and the volume, okay? So let's try that. Okay, so one of the first questions is Boyle's law. Boyle's law is P times V equals a constant, okay? So what I want to do now is I want to change the volume of this particular simulation, okay? So I'm going to move the volume down here. So you can see that as I click down here, you see that plunger is coming down, right? Now, what I want you to look at is here that the pressure number goes up, right? As my volume goes down, okay? So I keep going down in volume. You can see the pressure keeps going up, okay? The volume obviously comes down here. And you can, pause the video, replay it. You can see what's going on. Now, I asked you to answer this question. Why is pressure going up, okay? What is it about the simulation that tells you that pressure is now going up, okay? And again, you have to understand what pressure is, right, in this simulation. What is the parameter that corresponds to pressure, okay? So that again is the first question, is am I when I'm reducing volume, I can see that the pressure number goes up here. So the question is, why is that pressure going up? What is it about the particles? What is it that it's doing that's making the pressure goes up? Okay, so that's the first question. I want to ask the second question now, which is a pressure-temperature relationship. So now you see that I'm going to stay at pressure, so I'm going to still want to look at what happens to pressure. But now what I want to do is I want to change temperature, and all the other factors I want to remain constant. Okay, so let's see what happens there. I'm going to lower my temperature. So you can see as my temperature comes down, my pressure also comes down, right? The number goes down, and everything else remains the same. You can see that the volume remains the same. Nothing's changing. Why is the pressure coming down? Okay, what is going on? What's happening with these particles that the pressure is now coming down? The third question I want to ask now is volume temperature relationship. That's Charles's law. Remember that V over T is equal to constant. So I'm going to move this down to volume. So in other words, I want volume to change as I'm changing temperature. Okay, here I'm going to lower the temperature, and you see that as I'm lowering temperature, what's going on with the volume value? You can see that the volume value here is also coming down, right? And you see the plunger slowly comes down. Okay, so the question is, why does volume have to come down to balance that temperature decrease? Okay, think about what's going on here. Why does the volume have to come down? The last law I want to talk about here, you can also explain using this simulation, is Dalton's law. So if you remember, Dalton's law is it's pretty interesting. Dalton's law says that the total pressure in a gas is equal to the partial pressure of one gas plus the partial pressure of the second gas, and so on. Okay, I can prove that to you here. Okay, you see here that pressure right now it's 1 atmosphere, right? And I have 1 mole of helium right now. Okay, so if I were to increase the number of moles of helium to 2, you see that now the pressure is 2 atmosphere, 2.02, and there's more helium here, right? Because I let in some more helium. Okay, so let's reset that. So you remember that the total pressure was 2 for 2 moles of helium. Reset that. Instead of adding 2 moles helium, I'm going to add 1 mole helium and then 1 mole neon. Now neon is a bigger gas. Okay, we know that because the molar mass of neon is about 20, molar mass of helium is about 4. Okay, so I'm going to add the neon in. Neon are these bigger blue circles. I'm going to add exactly 1 mole of neon to this thing. So now you see both neon and helium are present. Okay, you see the total pressure is 2.02, which is exactly the same as when we have 2 moles of helium. Okay, you don't believe me? You can play back that video when I added 2 moles of helium instead of 1 mole of helium and 1 mole of neon. Okay, you have the same exact number. What that does is just demonstrates Dalton's law. Dalton's law says that the pressure, total pressure, is equal to the partial pressure of gas 1, partial pressure of gas 2, and the partial pressure depends on the number of moles. The question is why? Think about it. You have something that's a lot bigger. This neon gas particles here, they're a lot bigger. And generally speaking, if you think about a situation where you have something that's a lot bigger, has a bigger mass, right? They also have a bigger force, right? So if you think about a collision between a motorcycle to a wall versus a big truck versus to a wall, that truck is going to create more damage because the truck comes in with a bigger force. That's not the case with gases. We see that whether you're adding 1 additional mole of helium or you're adding 1 additional mole of neon, you get exactly the same effect, which is the same total pressure. So the question is why? That should be pretty apparent from this simulation that is going on right now. Again, when I have 2 moles total, 1 mole helium, 1 mole neon, I get 2.02. What explains that? Why is it that adding something that's bigger doesn't make a difference in the amount of total pressure that the bigger particles contribute? Okay, it's the address for the simulation at Oklahoma State, and you just need to have Java installed in your browser in order to run